much. My name is Giorgio Calarco, and today the aim of my presentation is to discuss the most relevant results related to the study of a mobile emergency operating center based on virtual networks. And first I will talk about the emergency networks in general, and then I will introduce the architecture of the emulation testbed that we developed during the past 3 years. And then I will focus on the main results related to the performance of the testbed during the emulation of an emergency network. And finally, I will report which are the testbed performance and constraints and the improvements that could be introduced in the near future. And first, let me focus on what is the architecture of emergency networks in general. And as you can see, we have a certain number of first responders, which normally act in remote areas with disrupted or limited communication infrastructures. And they are in the need of exchanging information with the Mobile Emergency Operating Center, the MIOC, and with the Remote Emergency Operating Center to enable cooperation and coordination at all levels. And of course, this is just a logical schema, and many possible topologies and technologies could be involved. And for instance, the European project ISPONDER has chosen a multi-layer architecture where different networks are employed together. And for instance, we can have a personal area network with wireless sensors, and an incident area network with a Wi-Fi or WiMAX connections between among the first responders and the MIOCs, or between two possible MIOCs. And then we can have a jurisdiction area network where the satellite link or possible infrastructures could be used. And then an extended area network which acts as a backbone for the jurisdiction area networks. And in particular, the MIOC, the Mobile Emergency Operating Center, is the key component of the emergency network since it is in charge of transmitting and routing information about, among all the personnel operating on the field and the command and control centers. And to do so, we have envisioned that it could be provided by several different radio interfaces, ranging from 3G to Wi-Fi or femtocells, WiMAX, and DVB RCS for the satellite link. And let me say that the study of this complex network is a quite difficult task. And our main goals are to determine the performance limits of the infrastructure and verify if this proposal is flexible, scalable, and reliable for our purposes. And then to study end-to-end QoS or security schemes. And to do so, we want to respect the traffic patterns of the applications we want to support. And so, to evaluate the performance of this network, of course, we need an assessment tool to evaluate and compare possible different architectures and to guide the development of the ISPONDER platform. And the first problem is which tool to choose to do so. And possible approaches are analysis based on queuing theory, which is ideal but difficult to apply to complex scenarios. Then we could use simulation, which is flexible and cheap, but not so useful for the implementation stage, and usually it requires a huge amount of computing resources for complex scenarios. And another possible approach is based on physical test beds, which are, of course, very realistic, but also expensive to deploy, and certainly not suitable for a priori evaluation. And then we could also use hardware emulators, which are based on ad hoc equipment. Usually they are very realistic, but also very expensive and not open to modifications by the researchers. So the choice, to resume, should be that an ideal tool should be as realistic as a physical testbed, as flexible as a software simulator, and as scalable and modular as a hardware emulator. So our proposal was to follow a hybrid approach in which software and hardware components are mixed all together, and to take the main benefits of both the different techniques. And we decided to use virtualization techniques to run software emulators and create what we call virtual networks or netboxes. And these netboxes are designed to be interconnected and cascaded together, and even with the external physical equipment. And let me resume here which we think are the main benefits of a hybrid approach. It can be flexible and open to future integrations. It can offer realistic performance and repeatable evaluation. And it's closer and a technological point of view to the final equipment. And moreover, it allows a step-by-step deployment toward the final prototype of the network. And let me first illustrate how is the traditional approach to network emulation. Usually, in literature, you can find this kind of scheme in which we have virtualization techniques used to run different applications, for instance, client and service applications. And usually the emulation is run within the host operating system. It's a single emulator which can connect the applications all together. And of course, this scheme is acceptable in principle, but when you want to emulate a complex network within this single emulator, it requires a lot of computing resources. So there are many research groups which found different solutions. For instance, you can split this emulator in different emulators and allocate these emulators on different PCs. And this brings to a distributed test bed in which you have several PCs coordinating and working together for the final result. But this scheme doesn't take into account that modern architectures, modern platform, modern hardware, it's usually now based on multi-CPUs and multi-core schemes. So we decided to follow this new approach, and this is a very important slide. As you can see, the scheme is quite different from the traditional one. We have a virtual container, and inside the virtual container we run the emulation. So the paradigm is reverted in comparison with the previous scheme. And if we allocate several containers, which is possible in a multi-core platform, we can use all these containers to run several emulators in parallel. And we used Ethernet as the glue to bind all these containers all together and to allow packets to flow between and among the different containers through these bridges, and possibly using the physical interfaces to connect the emulator to an external entity, an external element. So this scheme offers several benefits. It's modular. It can be accurate in the modeling of different network standards. It can support real-time emulation. It's open, since it can be interfaced with different external equipment or networks. And it's also very cheap, since it's based on commodity hardware and off-the-shelf software only. And let me now introduce the software tools we used. First, we employed the NS3, which is one of the fastest simulators around, and it can also act as a real-time emulator. And then, as a virtualization technique, we used Linux containers, which are very light since they allow to virtualize even a single application alone. They do not require the installation of the whole operating system as VMware or Xen or other tools do. And in principle, we could also not use the virtualization, but it's something that we have preferred to do since we can use virtualization to assign to each emulator a certain control amount of resources, CPU, memory, network interfaces, and so on, so that this emulator believes to run on a single distinct PC. And it's important to note here that we have used bridges to interconnect the emulators all together. But in the last slides, I will show that we also have tested a new technique to remove them and to improve the performance of the testbed. And okay, this slide shows an overview of the whole testbed. We have the emulation platform here, and which is connected by gigabit links to an external IP router. And inside the emulation platform, we can build several containers, and in each container, we can run a different emulator. So that it's quite easy to reach this result. For instance, we can generate a traffic flow from a Wi-Fi network, route it through the IP router, and then send it to the satellite emulator. And very briefly, let me just sketch the components that we have been used to create the testbed. The hardware is based on a dual Xeon quad-core PC with a PCI Express I/O bus and 4 or 6 Intel gigabit NICs. And for the software part, we used Linux 2.6, Linux containers, and NS3.9 emulators. Let's now move on to a very important topic, the emulation of the responder network, the emergency network. This is the reference scenario where we have a certain number of first responders connected through a Wi-Fi network to the commander, and the commander is connected to the MIOC using a WiMAX link, and then the MIOC is connected to the EOC through a satellite connection. And this real-world scenario is translated in our platform in terms of netboxes. We have a first netbox with a Wi-Fi emulator, then a WiMAX emulator, and then a satellite emulator. And it's worth noting here that we can employ real applications within these PCs, this one and the other one. And for instance, we have used LeanPhone, which is quite well-known VoIP application to generate the audio flows which are traversing the whole infrastructure. Well, these are simply the traffic profiles that we have used, but the most important thing is that we have applied different QoS scheme within the WiMAX segment, so that bulk data is treated as best effort traffic with a low priority. The audio communication is managed with RTPS, and the video flow is managed by UGS, which is the policy scheme with the highest priority. So very close to what could happen in reality. And what was mainly important for us was the realism of the outputs that we were obtaining. And these are the results of the first test that we have performed. Mainly, we are keeping the commander and the MIOC at 500 meters in this first test. And just to see if everything was working as we expected it to do, the WiMAX good put is quite high, about 7 megabits per second. And we injected about 800 kilobits per second of traffic. And as you can see, the, 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 the video flow is perfectly conserved, the audio flow is working well, and just the bulk data is affected by a perceivable delay. Then we increased the distance between the commander and the MIOC at 2.5 kilometers, so that the WiMAX capacity is lower, just 2 megabits. And as you can see, the video flow is still treated with a very low latency, and the same for the audio flow. But you can observe that the bulk data, the best effort traffic, receives a higher latency. And then, finally, in this slide, we bring the MIOC at 7.5 kilometers. And the WiMAX capacity now is reduced at just 700 kilobits per second. So the WiMAX link gets saturated in this situation. So you can notice that the video flow is still well preserved by the UGS scheme, but the audio flow is slightly degraded, but instead the bulk data, the best effort traffic, receives a very high delay, about 1 second of delay. So what is important for us here, the lesson that we learned, is that the emulation platform behaves very realistically. And more important, it's in full agreement with the experimental trials reported in literature. So evaluation can even be more sophisticated. For instance, here we have the return and forward channel of the emergency network where we apply different QoS schemes. This traffic is treated with the best effort scheme. As you can see, the latency is uniform, is uniformly distributed. Whilst in the return channel we have the QoS schemes that I showed you before, and you can clearly see the difference in how the traffic is managed. And of course, the same can be seen for the jitter. So, what I want to stress here is that for us it was important the realism of the platform and that it was behaving exactly as we expected. And another point to stress is the scalability of the testbed, and to stress the platform, we scaled up and we increased the number of containers. In these experiments, each container is generating traffic at the maximum speed. And as you can see, as we increase the number of containers and generators, the performance increases linearly. And this means that containers are insulating the emulators effectively and with no co-interference among them. And let me now move to some results that are important for the future. I showed you before that we were connected emulators with bridges, software bridges, which are software elements out of the emulation scheme. And we measured the overheads introduced by these bridges and for each of them. And we measured that they add about 90 microseconds of overhead. So we tried a new technique called the virtual Ethernet peers, where bridges can be totally removed and the latencies can be reduced to just 3 or 4 microseconds. And this is good result, but however, it's not always enough. For instance, it would be not enough if we wanted to emulate a gigabit network. That extra delay would be too high. And so this mainly the last slide. We wanted to understand which were the causes of these performance constraints, and we experimented a chain topology of containers up to 16 gigabit Ethernet links. You can see that the global throughput, the blue bars, are increasing, but the throughput for each network is decreasing. And the same is for the CPU load. And this means the bottleneck of the platform is not due to a lack of computing resources, but there are other factors. which we have analyzed. For instance, these are two manufacturers locking of the shared data within the kernel and CPU cache pollution. But the major limitation is due to the copying of packets between the kernel and the user space, and vice versa. So this is a very expensive task, which reduces the performance of the testbed. And currently, 3 or 4 microseconds are the best we can do. The only option would be to jump, to cut out the kernel from this processing. And currently, it's not possible yet, but new techniques are arising. For instance, the NetMat library, which allowed the user space application to directly control the network card. And this could lower these overheads to just a few nanoseconds. So this is probably the future for the testbed, I think. So let me just summarize this discussion of today. We started from the problem of the design of an emergency network. We said that it's a quite complex task. And the testbed was proposed as a solution for the investigation of this network, and it's based on containers and an S3. We show that it's modular, real-time, and interoperable, flexible, open, and scalable. And we analyzed the performance capacity of the testbed, and we investigated the bottlenecks and possible solutions to apply in the near future. And this is probably the future for the testbed. So that's all, and many thanks for your attention.
Thank you for your presentation. Any question? So if you want to summarize the main result of your work is, in a few words, is the development of a new low-cost tool for simulating a very complicated network infrastructure.
Yeah, mainly it's the design of a new scheme where we can use different components like containers and emulators, and in a way which was not used before. Usually the scheme is different, and we can take some benefit from the multi-core platforms and use them to parallelize complex networks and make emulation in real time and to study real applications and to see how they
if one PC is not enough, you can, of course, you can combine multiple PCs.
Yeah, of course.
Which is something to be avoided if possible.
Oh, it's not, this is not a problem in general because we use Ethernet to combine these elements, so it's just a problem of connecting two different PCs together. Anyway, multi-core platforms now are very cheap, and this testbed costs now about 600 or 700 euros. So
no, it's not much. So thanks again. So the next candidate of this morning is Mr. Marco Fei. You can start. No, do you have a? Okay, you can use the other microphone.
So